Okay, well, perhaps 20 minutes over, I realise it's the end of a day and I'm not going to put too many big equations in front of you. What I'd like to do is to tell you about the application of finite gap techniques to a very old problem that's actually constructing solutions for monopoles. And I'll write down the equations in a moment. I'm going to, in the beginning, just assume none of you are finite gap experts. So for those of you who are, if you can just sit back and enjoy it, I'm going to, because of the nature of most of you here, I'm going to give a parallel between the monopoles and constructing the sigma models that are relevant for various ADS cross spheres. So I'm going to tell you about some generalities. The important thing, I guess, is that the finite gap is really a conceptually beautiful framework, and when it comes to application, it's hard. So I'll give you the conceptual framework, and then I'll introduce you to a curve that's rather beautiful and tell you about some specific things. So we're always going to begin with some equation. So what I'm after is I'm going to try and solve the following equation that you'll all know from. So this is the equation of the monopoles. I'm going to be interested in SU2, charge n, and you can think of this as coming from a reduction of the instanton equations. I'm solving, everything is going to be classical. You can also view this as the Prasad-Sommerfeld limit setting the potential of a Yang-Mills-Higgs system to 0. And you should have, this is going to be the first set of equations, and the other we've seen several times. We have Mara-Cartan equation, and we have something like this. So we should be thinking of these as coming from an action, and in principle there are other terms. So I'm going to actually, the finite gap construction will give us a solution of these currents that satisfy the Virasoro constraint. So we have our equation, and the first step is to have isospectrality. So one of the highlights of the 80s was the Nahm transform that told us how we could construct these explicitly in terms of a set of coupled ODEs. So if you could solve these ODEs with the appropriate conditions I'm going to give you, then you would be able to reconstruct a monopole. So these matrices, the charge n feeds in, so these are n by n matrices. They're going to be regular for S in the interval 0, 2. And they're going to have simple poles at 0, 2 with residue and irreducible representation of SU2. So if we do this, all right, and we need certain hermiticity properties, we'll need Ti Hermitian conjugate of S to be minus Ti of S, and something on the transpose. So if you could solve for those equations, then you would be able to reconstruct a monopole. And I'm not going to give you the equations that would do that, but really this data can be put together into a form that you're happy with, a lax equation. So I'll introduce A of zeta which will be T1 plus IT2 minus 2I zeta T3 plus T1 minus IT2 zeta squared. So zeta at the moment is just a complex parameter, and we discover that we have the following Lax equation. Likewise, with our second R sigma model, we can group things together. We can introduce a current capital J, little j plus Hodge star j x over 1 minus x squared. We'll discover that we have a flatness for the connection, which will give us back both sets of equations. And if we have a flat connection, then we've seen several times already that we can introduce the Wilson loop associated with this. So we have the path-ordered exponential, and let's do it at fixed time, fixed tau. If we do this, then we have, at least in my conventions, something like this. And we again have a isospectral equation. So having got an isospectral equation, we then get our spectral curve. So in this equation here, it's quite straightforward. We're just going to have a polynomial in eta and zeta, det eta plus a zeta equaling 0. Now, if you go through what I've said, firstly, this takes the form of eta to the n plus a1 of zeta eta to the n minus 1 plus an of zeta. And just looking at the definition of A, you have that the degree of AR is less than or equal to 2R in zeta. The spectral curve that comes from the sigma models here is a little different. So we may want to just think of something like this. The problem is at the moment that we don't have an algebraic curve. We have here, well, so I'll think probably very concretely in terms of S3 and make remarks on SO6 and some of the others. So at the moment we can diagonalize, as we've heard, our Wilson loop in terms of, so it would be diagonal in terms of the quasi-momentum, thinking of SU2. And this isn't an algebraic equation. So since KMMZ, well, this has actually appeared a long time ago when people studied harmonic maps and various approaches, for example, given by Hitchin, tell us how to actually get a algebraic equation from this. And I'll come back to that later. I should point out that in many integrable systems, you don't always get an algebraic equation. The spectral curves could easily be expressed in terms of theta functions, very far from algebraic. So this isn't a killer, but you need to think about it. And we know from Seiberg-Witten theory that these spectral curves often have a physical significance in terms of branes. Now, what I would tell all my students, the first thing is when people write down a spectral curve is what are the coordinates involved? And that typically involves a surface. So I'm not going to dwell on this, but you should ask what it is. So we have here a set of coordinates, zeta and eta, and in fact we have eta d by d zeta. These are coordinates of the TP1 mini twistor space, the tangent space to the 2-sphere. For here, the standard situation is that we think of this as being an affine chart of P2. But there are lots of, again, always what is a surface? There's a huge variety of surfaces out there. So you can have Hitchin systems that will be the cotangent bundle to a curve. You can have K3. Tim Hollowood and I have a nice one with abelian surfaces. All that's needed is that you have a Poisson surface. And the reason I mention this is that, again, there is a strong connection between separation of variables and the Hilbert scheme of points, of a certain number of points on our surface. So we won't dwell on this, but this also comes in various aspects of string theory, because really we have a surface, we have a line bundle over it, and this total space X is in frequent circumstances viewed as a non-compact Calabi-Yau, and you've made the right choice of what L is. Okay, so that was an aside. For our curves, let me just note, let me remark here, the genus of this curve is n minus 1 squared, where n is a charge. So the genus grows very quickly. In the construction of this, we've heard that we want to view, in some sense, the number of degrees of freedom as being relevant for the genus. But you discover that when you, for example, look at the papers of Kazakov and collaborators, the genus of this actually grows relatively quickly in the number of cuts, and so you have to put constraints on it. But a caution to bear in mind is that the genus, you can check. So let's take a simple example. Let's take affine Toda theory. Affine Toda theory is in some sense purely Lie algebraic, and yet you can choose which representation you might wish to express your lax in. If you do that, you discover that the genus of the curve depends on your choice of representation. That's a fact. It's a bit upsetting, and so by changing representation, you can change the genus of the curve. The way you can understand that is that actually the flow that you get when you solve for the motion isn't actually seeing the full Jacobian of the curve you get, it's just on some small part of it. But there's a general caution, and you see it at this, just changing a representation can change a genus. Okay. Now, the next ingredient that we have always is, so if I use this board over here, are the people at the back going to be complaining? No. Reality. So the curves that we get are not just complex, they typically come with a real structure to them. Now, for the monopole, that has a physical picture. What's TP1? TP1 is just the space of lines in 3 space. And the mini twistor construction of monopoles came from looking at a scattering problem along the line, and you wished to know which lines you had decaying solutions at both ends. And that gave you the spectral curve. And clearly that's invariant under the exchange of the line, the orientation of the line, and that gives us a real structure on the curve. Similarly, for the sigma model that we have here, well, if you look at what this means for the coefficients, this will mean that AR is expressible in terms of 2R plus 1 real coefficients. And for the sigma model, we have the Hermitian conjugate of J being minus J. This will lead to a constraint on the Wilson loop, and ultimately it will tell you that you have your branch points as complex conjugate pairs or real. And that fits in with the pictures that we saw yesterday, where we saw at various times simulations of the roots coming in along the real axis and then splitting off in complex conjugate pairs. I should point out, you may not know, but having a real structure constrains the period matrix. Constrains the period matrix. And I will come back to the period matrix. For the situation that we're working with here, where we can actually write down what the polynomials are, the real structure is easy to implement. But actually, this is one of the hard points if you were to be looking at, for example, solutions of KdV or Kp, is how to get curves that actually have that being true. Okay. The next ingredient, and almost the last, we need to define flows, right? We have a Hamiltonian, and I'm going to need to describe a flow, and that's going to be done by various meromorphic differentials. And in some sense, when we've written down lax, we've told you what those differentials are going to be. Because here, well, you'll see that you have essential singularities here at x being plus or minus 1, and I'm going to be interested in differentials that will have just pole behavior x minus 1 squared. Now, okay, so x isn't, I haven't actually described, I have to tell you what a point is on the curve. So just telling you what x is hasn't told you what a point on the curve is. There will be, for y tilde there, various points on the curve. If in the S3 case, the natural one is you have a hyperelliptic curve, and I would have to define what this differential is at the various singular points. For the monopole, so for the monopole, you can see that something goes wrong at infinity, and I'm going to define a meromorphic differential coming from, because of the essential singularity that's going to appear at infinity. So again, it's an exercise just going through what's on the board and no more, that you can see that at infinity, eta over zeta, just looking at this characteristic polynomial, it must go like rho j of zeta. For some number rho j, that's going to be a root. This is an n-sheeted cover of the plane. So there'll be n over a specific zeta, there'll be n values of eta. And this means that d of eta over zeta looks like, well, if I write a local coordinate, zeta being 1 over t, then I have minus rho j over t squared plus regular dt. and I'm going to define a differential that's going to be the important thing, gamma infinity, which will be rho j over t squared plus regular dt at this point on the jth sheet. So given these two differentials, we're almost there. We have a set of period constraints. So I haven't defined explicitly for you what these differentials are until they're not defined uniquely at the moment. I've told you what their pole behavior is. We define them uniquely by requiring, say, their A periods to vanish. So this will define for us, at this stage, a unique differential. So again, I have a basis of my homology with some pairing A and B cycles that pair, and they don't in that fashion. Now, yesterday we were told, so this at this stage has defined for us a unique differential. It defines for us a particular flow. It's essentially telling us about the Hamiltonian that we're interested in. And we were told yesterday, just for periodicity of our solutions, we wish this to be 2 pi by some integer. The monopole is just a little different. We have a vector that I'm going to call the Ercolani-Steiner vector. Ercolani and Steiner were the first people to apply finite gap integration to the monopole problem. And okay, so this sits in the period lattice. The Ercolani-Steiner vector itself doesn't sit in the period lattice, but you'll see I've had something on the interval 0, 2, and that 2 is precisely what causes I wish to have 2u to be in the period lattice. So this means that u takes the form half n plus tau n. Now, this is actually a hard point, and that's what I'm going to come back to. We just write this. This constrains a curve, and we can show that there are always curves. We can often show that there are curves that satisfy these, but I ask you to give me one, and in a short while you'll see just how hard it can be. So essentially it's this, trying to solve this with what I've said, that would be almost enough to give you a monopole, and yet you can't solve it. I'll describe the lovely mathematics that's involved. But
physical interpretation of integers n and m that characterize different solutions in the monopole case?
well, they will give you different monopoles. Yes. Can I come back to that in a short while? I'm not telling you apart. There's another way to understand these functions in terms of algebraic geometry, and I don't really want to jump into that language until the end if I'm pressed. And I know I'm going to be pressed on time, even starting when I did. You can count the number of parameters involved. So what's this doing? These are placing G constraints on our problem. So you could just sum up. So how many degrees of freedom do I have on the monopole? I have sum of AR. A1, the coefficient there is in some sense the center of the monopole. So if I summed R equals 2 to n, take away the genus, and you'll get 4 n minus 1. And that's a reflection that the moduli space that we're dealing with is hypercalar. Okay, the final ingredient with all of this, well, there are the final two ingredients. There's a function called the Baker-Akiza function. So in rewriting this so that I didn't put up too many awful formulae, I decided that, at this time of the day, either you're very tired like I am, or if someone puts up some theta function expressions, it will just put you off your dinner. So I'm going to tell you what this. All Baker-Akiza functions essentially have the same form, and when you look at them, you know, they can look pretty intimidating, but there are just two salient features to always look for. But I'm going to use the Baker-Akiza function. What it is essentially is an eigenvector of either my lax or my monodromy. Using the eigenvectors, I can reconstruct the lax or the monodromy, and hence get a solution. So a part of the story I'm not going to tell you about is the reconstruction, but I'll say it in words later. And there is an issue that you should always ask, and that's the regularity of the solutions. And for the monopole, that's going to be the thing that hits us. Okay. Just a word on Baker-Akiza functions. So you remember from your undergraduate days that if you had to write a function on an elliptic curve, you could express it in terms of at least a product of 2 thetas over 2 thetas. But you have to have at least 2 thetas. At least that's what I teach my 4th year students. And Riemann has a generalization of that to an arbitrary Riemann surface, but you always need, as a basic building block, at least 2 thetas in a numerator and 2 thetas in a denominator. And the reason for that is that if you just have one, the theta functions are quasi-periodic, and you cancel the phases by having a balance between thetas in the numerator and denominator. The key all Baker-Akiza functions essentially, though, are built out of 1 theta in a numerator and 1 in a denominator. So phi here is the arbor map that I'll have to come back to at some stage. And to get rid of the quasi-periodicity, we would have, in my situation here, our differential, the differential that we're interested in, and a combination of these B periods here with what appears in here will give you something single valued. And I should put in, so really we want a time, so I've called it S. I should probably have SU. And just make this D. So this is for some point in the Jacobian that I will have to tell you about in due course. And the other part of the Baker-Akiza function is just a function that's purely on the curve. So with those background, those are the essential ingredients that go into everything that you need if you're going to use finite gap integration. And it's this point here, before I lose it, that I'm going to talk about, and a lovely result of Ramanujan. So while I'm waiting for this to fire up, I should say that if you have a Riemann surface, there are several things that
Can you press
which button now?
computer? Oh no, it's coming.
Good. So what I'm telling you about now is joint work with Victor Anolsky. So I'm going to introduce you to a curve. I'll tell you about one and possibly more monopoles and a result of Ramanujan. So the curve I'm going to tell you about, everything that you've heard in the talk so far have been essentially about hyperelliptic curves. So I'm going to introduce you to something just a little more interesting. The trigonal curve, so Zn curves were looked at in the 80s when people were wanting to do various conformal field theories related to more interesting surfaces. And I'm going to treat this simplest curve. The reason I'm choosing it is that this curve has a symmetry. It's got this rotation by a cube root of unity. it's absolutely straightforward to write down a set of differentials on a curve, of holomorphic differentials on a curve, and what's needed at some stages is to normalize these. Integration is the hard point. We need to have a set of homology cycles. Now, in the late 70s, the topologists Tretkov and Tretkov gave us an algorithm to construct this, but the algorithm, if you typically apply it, is never going to tell you about symmetries. And so we've heard about giving problems to graduate students. So I've given such problems to graduate students, and it takes a while for people to figure out how to implement symmetries on the homology cycles. I have 3 sheets here, so how should you look at this? You should see the full curve here is on sheet 1, the big dash on sheet 2, and the dots on sheet 3. The big difference between the hyperelliptic case is that not all branch points just take you between 2 sheets. Here, the monodromy around these branch points take you between 3 sheets. And indeed, the vast majority of curves that you will get in studying integrable systems aren't just branch points. The arguments that I've read in your papers are that you are always interested in generic situations, but there are interesting points in the moduli space, like the Argyres-Douglas point, that are not generic. And so you need just to be aware that interesting phenomena can happen when you get these coalescence of branch points. So I've written down a series of A cycles. The B, if I've got 3 sheets, I just get the same contour and I just drop it down a sheet, and that will give me B. And you can see there's a clear symmetry between A1, A2, and A3, and the hard one to pick out is A4. So given a set of contours, you actually have to do something at some stage. You have to integrate. But before we integrate, let's just think about the symmetries that we have, and that's going to simplify the problem. So X is integrating whatever it was, du over w around each of the cycles, and like for the others, using the symmetry we have, we actually discover that we can relate the integrals of the B cycles to those of the A. And that, for this curve, is a great simplification. I have a period matrix. There are 2 possible normalizations. I'll give one. And I'll just observe that if you use the bilinear relations, it actually gives you a degree of orthogonality between the columns of that. Okay, so I need a period matrix. Now, you should be alert to, again, when you've gone away from hyperelliptic curves, I essentially can name the curves that you can actually write down a period matrix for. There are a couple of families, but it's hard. There aren't many. This is one. So Wehlstein did this in 1899. Matsumoto's come back to it. This curve again has interesting properties, and I have to say, so Wehlstein, it's a lovely paper, but they didn't have matrix notation at hand in those days. And if he just knew the word cofactor and so on, his paper could be written, and well, Victor and I have got essentially a 4-line proof of this, but we knew about cofactors, and he didn't have that language. So we can write down the period matrix. The thing to observe about this is that this period matrix only depends on this one set of cycles, these integrals x. I can solve for this transcendental constraint that's now disappeared in terms of these. The point, and I should point out that this is the only class of curves that this has been done for. So this took some work. What should you glean from this? You can solve for this transcendental constraint if you could solve an equation like this. This actually means that the periods that you have are rational. So it's already telling you that what you're seeking is a rather rare thing. Can we ever solve it, though? So for the quick remainder, so you don't miss your dinner, I'm going to limit myself to the following class of curves. So it's got the 6 roots there are related. I've called them alpha and beta, and they're related So we need to actually do some integrating. So there are some people here clearly in the audience who like integrating, and that's always the hard thing to do. So what I gave you these strange figure-of-8 contours. That's actually the generic shape that you will always get for contours when you use this algorithm. And what I will do is I will express that figure-of-8 contour as an integral, say, from the origin to a root, back on the next sheet, out to the other, and back. And that will express everything in terms of these two integrals. And if you, that line there would just tell you I can express each of these integrals in terms of each of these periods in terms of two basic integrals.
What is W in the integrand?
So W was the scaled piece that got rid of this chi. So I think I defined W to be either eta chi to the minus a third or such. So W is essentially eta, but I want to get rid of this chi. So one discovers that these integers that you get are not totally unconstrained. They're related. And let me just bring up what we're trying to solve. So what we have to ultimately solve is the ratio of two hypergeometric functions being an appropriate rational number. These are the Ercolani-Steiner constraints. This is what it requires for us to have this integral, the analog of your integral dp in the period lattice. So this is why I'm telling you that they're transcendental, and you ask yourself, could you ever solve for that? And, well, first thing to do is to, so this just brings together, you can solve everything that you need if you can solve for that ratio of hypergeometrics being rational. So let's, is that visible? So this is this ratio of the hypergeometrics. So clearly every rational number is in here. Can we ever solve it? And this is where Ramanujan comes in. So there was a man in Chicago, Bent, who essentially his life's work was to go through the Ramanujan's notebooks and to have he and his graduate students and postdocs fill in the gaps. And we're coming to one of the very last gaps that was filled in. It was only filled in the late 90s. Ramanujan wrote down in his second notebook a series of very wonderful, I think about 16 wonderful formulae for 1 over pi. And then a cryptic remark and how it could be generalized. And it was this cryptic remark that took until the late 90s to understand. And the reason this half a half, well, we'll come to that for those of you, but the 1/3, 2/3 should sort of remind you of what we had in that hypergeometric. I had a 1/3, 2/3 entry. So something that's probably just worth knowing, modular transformations. So everyone here is very happy, I think, with elliptic curves. So the complete elliptic integral is a hypergeometric with half-half first entries expressed in this way. And a modular transformation will relate the parameters that you have for the two elliptic curves. So if I wish to say, how do I relate the argument of the hypergeometric, the modulus, when I double or when I treble? So a modular transformation is going to lead to an equation of this form. And here we have, if alpha and beta satisfy that equation, then you know that n is 3. And the generalization that was constructed essentially replaces just with 2 all of the numbers that come from the Platonic solids. So there's now a notion of a modular equation of degree r and signature n, and you'll see when we have 3, it's exactly of the form that we want. And key for us? Well, I'm going to identify this solution with alpha as a half with a particular monopole in a moment. So here is just a set of solutions. You can actually solve for the number theory. You can write down for what these integers are and what the parameters of your curve would be. I'm coming to an end. The tetrahedral monopole fits into this. It's got a particular, so I knew that there would be a monopole of this class. The tetrahedral monopole corresponds to this value that we've got there. Just as an aside, I mean, so you have to calculate a period matrix. So this curve was looked at by Nick Manton, Connor Houghton, and Ramau at some stage, and they had various numerical conjectures about what the period matrix of a tetrahedral monopole should be. Well, you discover that the tetrahedral monopole has a magnificent period matrix. It's very straightforward. Okay, so the last transparency, and we'll come back to. In the reconstruction, you are going to have to ultimately use theta functions. So there are good packages out there that calculate very efficiently theta functions. A part of the theta function I haven't told you about is that you would need to calculate a vector of Riemann constants for those of you who are expert. We can calculate it for this curve explicitly. Again, the number of curves that you could calculate a vector of Riemann constants is limited to 2 hands. The monopole is probably the toughest of the testing grounds for any of the finite gap integration because the regularity properties of it are very hard. So what this means for us is that this denominator, for example, it starts off, I said that there's a regular pole at s equals 0 and s equals 2. It means that this flow that you have cannot hit the theta divisor. It can't be 0 at any stage. And there's no way that anyone knows of implementing that. I mean, here's an absolutely straightforward question. I have a function, a complex function, and I have a line, and I want to know how many zeros are on that line. How do I do it? A real line. I've graphed it. I didn't know any other way. The tetrahedral monopole, no zeros. It survives. The other n and m that appear, they're corresponding to other types. They're corresponding to a line bundle. The line bundle has different values of different numbers of sections at points between 0 and 2. So that's what these n and m are actually telling us.
They're all continuously connected as well, right? Because they're all part of one modular space.
Yes, but the point is that they're not within this class of curves that I've chosen.
Yeah,
And
right.
although what you're saying is right, when we deform in that, all of the data that you have, your period matrix, your vector of Riemann constants, everything moves, and then you have to at each point be able to calculate those. So I'm for the purpose of this talk, I'm just wishing you to see that, here's a very attractive curve, but it's not, to actually calculate is tough. And so sadly the upshot is that this is not a monopole because it's not regular. Victor and I can conjecture, the number of zeros that all of these curves have, and we have no analytic way of knowing how to solve that. So I'll leave that for you. It's a simple, a simple problem. A complex function on a line, how many zeros does it have? Is there a simple way of doing that without actually integrating? So at this stage, I've reviewed the ingredients of finite gap integration. They're always the same. People write down for you this integral dp as 2 pi n or whatever. Actually, hidden behind that, if you were just starting from that side of the story, is something very complex. That's very transcendental if you want to get your hand on that curve. It may well be that the beta ansatz side actually gives you a way to say what those good values are. Now that's one of the attractions that you have, at least in this ADS CFT, is that you have two ways of looking at the same problem. But if you're just stuck with finite gap, although it's been around for 25 plus years, the reason you don't see many solutions is that there are these transcendental constraints built in, and we just don't know how to solve them. So I'll leave it there. I hope that hasn't put you off your dinner.
Questions? There are no questions left from this people yet.